All right, so this is section 12.5, day 2. We are now going to look at how to write the equation of a plane. We've already looked at equations of lines, so let's expand our knowledge a little bit. If you remember when we were writing equations of lines, parametrically or in vector form, what we needed was a point on that line, and we needed a direction vector that gave the direction of that line. Well, a plane it's a little bit, it's not too hard, but it's a little bit more difficult to describe with just a point and a direction. And the reason for that is because of the second paragraph here. A single vector parallel to a plane is not enough to describe the direction of that plane. There's many different planes that are parallel to that vector and pass through that given point. So you can have more than one plane. However, even though a vector parallel might not work, if we know a vector that's orthogonal to the plane and we know a point on that plane, that is enough to completely specify the direction of that plane. So this is really the highlight of what we need here. A plane in space is determined by a point on the plane. We'll call it P naught with coordinates x naught, y naught, z naught. And I'm going to highlight that down here as we look at the words. Let's look at the picture underneath. So here's the blue dot that I'm describing right here. That's P naught. And we need a vector that's orthogonal to the plane, which we're going to call n. And we're going to call that a normal vector. It's a vocabulary word we need to know. Okay, so a normal vector is just a vector that's orthogonal to that plane. Okay. And then how are we going to start writing the equation here? Well, let me highlight a couple things here. Here's the normal vector in pink. Okay, so there's n. That's coming, kind of think of it as like if you have a piece of paper. Here's my stylus. It's kind of pointing straight up out of the plane at a right angle to that plane. So that's your normal vector, would be my stylus, and the plane would be my piece of paper. Okay. Just like we did when we did equations of lines, we want to start at this initial point P naught, and we want to move in the direction of a general point. We'll call it P with coordinates x, y, z. And so then this vector here that I'm outlining in green would be P naught P. Okay. And if we connect a couple vectors here, I'm going to connect two vectors. If I connect a vector from the origin out to my initial point P naught, and I connect it, we'll call that r sub 0. And if I connect a vector out from the origin to my final point P, we'll call that r. Then that green vector, if I do a little bit of triangle inequality here, and remember tip to tail for vectors, then in order to get vector r, that green vector would have to be represented by r minus r naught. And you can check that. If we go tip to tail, from the origin out to P naught would be r0. The only way to get r as a resulting vector for the other rainbow vector would be if my green vector was r minus r naught, because then the r naughts would cancel and I'd be left with r. Okay? So that green vector is r minus r naught, and that's represented by starting at P naught and ending at vector P. Okay? And the normal vector, it's orthogonal to every single vector in the plane. So in particular, it's orthogonal to that green vector starting at P naught and ending at P. So it's orthogonal to r minus r naught. And so what do we know about the dot product? Well, if we have two vectors that are orthogonal, their dot product has to equal 0. We saw that in section 12.3. So our vector equation of the plane, the normal vector n dotted with that vector in the plane, r minus r naught, that was P naught P, has to equal 0. And so this is what we call the vector equation of the plane. And by expanding it, we will get a linear equation, or we'll call it a scalar equation of the plane. So let's give some of these vectors components. Okay, so keeping in mind, I'm going to put that back up at the top, what we just found. Normal vector dotted with r minus r0. This was the vector sitting in the plane. This was the vector orthogonal to the plane. That dot product has to equal 0. Okay, if we want to expand it, let's just say our normal vector has components a, b, and c. Let's say our final vector is represented by coordinates x, y, z. So that would be the vector that starts at the origin and ends at P. Let's say r sub 0 has coordinates x naught, y naught, z naught. That was the vector that started at the origin and ended at P naught. Then let's expand a little bit here. This would mean that a, b, c dotted with x minus x naught, y minus y naught, z minus z naught has to equal 0. And then using what we know about the dot product, we can expand this. So this would mean that A times x minus x naught plus B times y minus y naught plus C times z minus z naught, just using the definition of the dot product. That sum of products has to equal 0. Collecting like terms, we would get A, oops, let's try that again. We would get A times x plus B times y plus C times z. We distribute. And then I'm going to call the constant D equals 0, and I'll explain what D is. D is just going to be the collection of like terms, negative A times x naught minus B times y naught minus C times z naught. So that entire sum of products is going to be our constant. We'll call it D. So where D equals, I'm going to factor the negative sign out, negative quantity ax naught plus b y naught plus c z naught. Okay. And so this is what we call a linear equation of the plane. Sometimes you'll see they move the constant over to the other side. There's a lot of different ways. These are all different linear forms of the plane, whether you keep d on the left or move it over to the right. The point is it's not in vector form anymore. The fact that we've collected all the like terms together is what makes it a linear equation. Okay? And I would say this is the form that's most helpful for graphing because you can very easily find the x, y, and z intercepts and see a portion of that plane once you graph it. So we'll look at an example in a little bit that does that. Just like with linear or equations of lines we saw last time, these forms are not unique. You could have chosen a different initial point on the plane. You could have used any scalar multiple of that normal vector because it would still be orthogonal to the plane even if you doubled the size of the normal vector or cut the size of the normal vector in half. So choosing the initial point, rescaling the normal vector will change that equation of the plane. So it is not unique. Okay, let's look at an example with some numbers here. Find an equation of the plane passing through the point 2, 4, negative 1. So this is going to be our P naught. And orthogonal to the vector 2, 3, 4. So there's our normal vector. So we know that the dot product of 2, 3, 4, and then we want to create a vector that starts at P naught and goes to a final point P on the plane, x, y, z. So we want the vector P naught P. So we're going to dot this with x minus 2, y minus 4, and z minus negative 1. So z plus 1. These two vectors that I've written are orthogonal to each other, so that dot product has to be 0. So there's a vector equation of the plane. And now I'm going to write a linear equation of the plane. So 2 times x minus 2 plus 3 times y minus 4 plus 4 times z plus 1 equals 0. Collecting like terms, we get 2x plus 3y plus 4z. We end up with minus 4 minus 12 plus 4 equals 0. And collecting like terms here, what do we get? We get 2x plus 3y plus 4z. If you leave the constant on the left side, what do we end up with? Negative 4 plus 4 cancels out. So we end up with minus 12 equals 0. So that's one way you could leave it. You could also choose to move the minus 12 over to the other side. So you could do 2x plus 3y plus 4z equals positive 12. That would also work. So there's our equation of the plane. So pretty straightforward as long as they give you a normal vector. Sometimes they won't give that to you, and we'll look at an example where you have to find that yourself. They might just give you a set of points that lie on the plane. Let's do one graphing example. Find the intercepts and sketch the portion of the plane that lies in the first octant. This is still related to the last example we just did. And so let me just rewrite the equation of the plane we just found. So it was 2x plus 3y plus 4z equals 12. That was our plane. We want to sketch the portion of the plane that lies in the first octant. So remember, that means x, y, and z are all positive. And so the easiest way to do this is they even gave us a clue. They said find the intercepts. So if we find the intercepts, we'll just put them on the graph and we'll connect them together, and you'll see a portion of the plane. So if I find the x-intercept, I'm going to let y and z equal 0. So x-intercept, if I let y and z be 0, then 2x would equal 12. And so then x would equal 6. So on the x-axis, I'm going to go out 6 units. So this would be the point 6, 0, 0. The y-intercept, I'm going to let x and z both be 0. So I get 3y equals 12. So at the point 0, 4, 0, I'm going to go out 4 units on the y-axis, put a dot. And the z-intercept, I'm going to let x and y both be 0. So I end up with 4z equals 12, z equals 3. So at the point 0, 0, 3, I go 3 units up on the z-axis and connect these together. Let's do blue. So this would be the portion of the plane lying in the first octant. This is not the entire plane, right? The entire plane would be continuing on two-dimensionally forever in both directions, but this is the slice of the plane that you see in the first octant. Okay. All right. Okay, I mentioned this before. Sometimes they will not give you a normal vector, and you have to find it yourself. Find an equation of the plane that passes through the points 1, 3, 2, 3, negative 1, 6, and 5, 2, 0. And I graphed it over here so you can at least get a little visual. So in this case, we have a point. Actually, we have 3 points on the plane. So what do we need to make the equation of the plane? We need a point on the plane, and we need a normal vector. Well, we have 3 choices we could use for the point on the plane. It does not matter which one you use. So I'm just going to choose to use P as my initial point on the plane. And what I'm going to do in order to create a normal vector, well, how do I create a vector orthogonal to a set of vectors? I can create 2 vectors from this plane right now. If I fix point P, I know PR is on that plane, and I know PQ is on that plane. So PQ and PR lie on the plane. That's pretty clear just from looking at the picture. Well, if I want to create a vector that's normal to those vectors or orthogonal to those vectors, we have an operator that we've learned about that does that. It's called the cross product. Okay? So we are going to need our normal vector is going to be the cross product of these 2 vectors. So I'm going to start by finding PQ and PR. PQ, I'm going to subtract my coordinates. 3 minus 1 would be 2. Negative 1 minus 3 would be negative 4. And 6 minus 2 would be 4. And PR, subtracting coordinates, would be 5 minus 1 is 4. 2 minus 3 is negative 1. 0 minus 2 is negative 2. Okay. My normal vector is going to be the cross product of PQ and PR. And we'll see, we can use any scalar multiple of this cross product, right? We don't care as much about the length of this normal vector. We care about the direction. That's what this normal vector is contributing, is it's contributing the direction of the plane. So PQ cross PR, I'm going to set up my determinant, put my standard basis vectors along the top. I'm going to put PQ first. It really doesn't matter since we don't care about the length of this. 4, negative 1, negative 2. Okay, so let's go down here. We get I crossing off first row, first column. We're left with negative 4, 4, negative 1, negative 2. Minus J, cross off first row, second column. We're left with 2, 4, 4, negative 2. Plus K, cross off first row, third column. We're left with 2, negative 4, 4, negative 1. And so I end up with I times 8 minus negative 4 would be plus 4. Minus J times negative 4 minus 16 plus K times negative 2 minus negative 16 would be negative 2 plus 16. So we end up with 12, negative 20, but we have a negative in front, so positive 20. And 16 minus 2 would be 14. So you could use this as your normal vector, 12, 20, 14. That would be orthogonal to the plane. We can use any scalar multiple of n. Okay? So what do we need? We need a point on the plane. So we'll use P. You could use any of the 3 points. It does not matter. We'll use P and let our normal vector n equal, we could use 12, 20, 14, or we could scale it down in size. It does not matter. Maybe for this case, let's just use the original. No, let's scale it. So let's use, let's divide everything by 2. 6, 10, 7. Again, it does not matter. You could use the original as your normal vector. I'm just dividing out a common factor. Visually, what that would look like, if this was my original normal vector, if this was my cross product, all I'm doing is I'm using half of it. Notice it still is going to make a right angle no matter what size of the vector I use. So you can scale that normal vector down in size. Okay, so there's our normal vector we're going to use. There's our point. And so our equation would be, we're going to have 6, 10, 7 dotted with x minus 1, y minus 3, z minus 2 equals 0. And expanding, we're going to get 6 times x minus 1 plus 10 times y minus 3 plus 7 times z minus 2 equals 0. If you distribute and clean that up, you should get 6x plus 10y plus 7z equals 50. Okay, so same process we did before. The only added bonus is you have to find the normal vector yourself. And the way that you do that is you end up finding 2 vectors on that plane, and you take their cross product. Okay, example 3. What we got here? Find the point at which the line with parametric equations 2 plus 3t, y equals negative 4t, and z equals 5 plus t intersects the plane 4x plus 5y minus 2z equals 18. This one's a pretty straightforward process. We have an equation for x, y, and z to describe the line. So all we're going to do is substitute in those expressions for x, y, and z on the plane and solve for t. So step 1, we're going to substitute in x, y, and z. So 4 times x is given by 2 plus 3t, plus 5y, y is given by negative 4t, and minus 2z, z is given by 5 plus t. This needs to equal 18. Cleaning this up, let's see what we get. We get 12t minus 20t would be negative 8t. Negative 8t minus 2t would be negative 10t. 4 times 2 is 8. Minus 10 would be negative 2. This needs to equal 18. Negative 10t equals 20. So we know t equals negative 2. We still haven't answered the question. They want the point where the line intersects the plane. So now all we do is we plug it back in. So if I plug it back in, step 2, x equals 2 plus 3t. So 2 plus 3 times negative 2 would be negative 4. Y equals negative 4t. So negative 4 times negative 2 would be 8. And z equals 5 plus t. So 5 plus negative 2, or 5 minus 2, would be 3. And so the point where we intersect is at negative 4, 8, 3. Okay, other facts about planes. We'll have some questions we see that deal with this. Parallel planes, so planes that don't intersect. 2 planes are parallel. Well, that would mean that their normal vectors have to be moving in the same direction. So their normal vectors would have to be parallel to each other. How do we check that? We check to see if the normal vectors are scalar multiples of each other. That's how we check in general if vectors are parallel. So the normal vectors are, if you think back to what we did on the last page, the normal vectors are just going to be the vector of coefficients for x, y, and z. Just distributing that dot product. So are these 2 planes parallel? Well, let's call this first normal vector n1. Coefficients of x, y, and z would be 1, 2, negative 3. And for the second plane, n2, our normal vector would be 2, 4, -6. So you have to kind of just look at them and compare them. Are they scalar multiples of each other? Looks like, yeah, it looks like every single component doubled in size. 1 times 2 is 2, 2 times 2 is 4, -3 times 2 is -6. So yes. Okay. N1, or sorry, N2 is exactly equal to 2 times N1. So planes are parallel. Okay. If they're not parallel, then they have to intersect in a straight line. It's a property from geometry. If two planes intersect, then they intersect in a straight line. The angle between the two planes is formed, and it's defined to be the acute angle between their normal vectors. So if you look at the visual below, this angle theta, one of the planes has a normal vector n1, the other plane has a normal vector n2. This angle created here, this acute angle theta, that is the angle between the planes. And you'll notice it's alternate interior with this little angle down here, which is the same measure. So whether you look at it at the top or at the bottom, it's the same angle. Sometimes when you crank out these calculations, you might get an obtuse angle. The only way to correct for that is to subtract from 180. So if you end up getting an obtuse angle, just do 180 minus theta, and you'll be given the acute angle. Okay, find the angle between the planes x plus y plus z equals 1 and x minus 2y plus 3z equals 1. Okay, so based on what we said on the last page, we are looking for the acute angle between the normal vectors. So we need the normal vectors for each plane. Normal vector for the first plane, I'm going to call n1. Looking at the coefficients of x, y, and z, I have 1, 1, 1. And for plane 2, call this one n2, coefficients of x, y, and z are 1, -2, 3. So there's my normal vector for plane number 2. And recall how to find the angle between two vectors in general. If we want the angle between two vectors, we know that cosine of theta is equal to magnitude A times magnitude B. I'm sorry, dot product of A and B. A dotted with B is equal to magnitude A times magnitude B times cosine theta. And so cosine theta is the dot product of the two vectors divided by the product of their magnitudes. So we're just going to apply that formula using the normal vectors as our A and B. So cosine theta, the angle between the planes, is going to be the dot product of the two normal vectors divided by the magnitude of the first normal vector times the magnitude of the second normal vector. Taking the dot product, 1 times 1 plus 1 times -2 plus 1 times 3 divided by magnitude of the first normal vector would be the square root of 1 squared plus 1 squared plus 1 squared times the square root of 1 squared plus -2 squared plus 3 squared. Let's clean this up a little bit. So we end up with cosine theta equals 1 minus 2 is -1. -1 plus 3 is 2. On the bottom, rad 3 times rad 4 plus 1 is 5 plus 9 is 14. So we get 2 over rad 42. And then we want the angle. So we're going to take the inverse cosine of both sides. I'm going to give it in degrees. It didn't specify. On a quiz or test, I would let you know what I want. So if I put this in my calculator, let's see if I'm in degree mode. I am. Second cosine of 2 over rad 42. I'm going to round to the nearest whole number. Gives me an angle of about 72 degrees. And that is an acute angle. So that is the angle we want. If it was obtuse, again, we would want to subtract from 180. So this is about a 72-degree angle between the planes. Okay, last one here. Find symmetric equations. Recall what that means. That's x minus x naught over A equals y minus y naught over B equals z minus z naught over C. X naught, y naught, z naught are the coordinates of the initial point. A, B, and C are the components of the direction vector of the line. Okay, so just a recap from the last section we looked at. This is symmetric equations. So we want symmetric equations for the line of intersection of the two planes. So we have two planes here, x plus y plus z equals 1. It's actually the same two we were just looking at. And they intersect in a straight line. So here's I'm going to draw it here. These two lines intersect in this line that I'm outlining in a rainbow color here. And we want to find an equation for that line of intersection. Well, we need a point on the line and we need a direction vector. So those are the two things we need before we can write the equation of a line. We need a point on the line and we need a direction vector. So maybe first thing let's do is let's start by finding a point on L. Need a point on L. There's different ways you can do this. What I usually try to do is find the point that intersects one of the three most popular planes, either the XY plane, the YZ plane, or the XZ plane. So I'm going to do an easy one. I'm going to look for where L, I'm just going to look and see where it intersects the XY plane. So I'm going to let Z equal 0. So if I look at my two equations of the planes here, I'm going to plug in 0 for Z here, and I'm going to plug in 0 for Z here. So I'm looking at the system. Means x plus y would need to equal 1, and x minus 2y would need to equal 1. Subtracting the two equations, do a little bit of elimination here. I would get 3y equals 0, so y would equal 0. Plugging back in, x plus 0 equals 1 means that x would have to be 1. So we know that 1, 0, 0 is on L. Okay. So that's it. Now we know a point on the line. So I'm just going to make a note here. This is a point on line L. Okay, now we need a direction. This is the part that you have to think about a little bit more. Well, looking at it, remember that that line L is in both planes, right? So that would mean that it has to be orthogonal to the normal vector for the first plane, but that line also has to be orthogonal to the normal vector for the second plane, because the normal vector is going to be orthogonal to all of the vectors in each plane. Well, if I need to find a vector that's orthogonal to the first normal vector, but it also is going to have to be orthogonal to the second vector, since this line is on both planes, then I can take the cross product of the two normal vectors. Because what does a cross product give me? A cross product gives me a vector that's orthogonal to two vectors. If I'm going to use the two normal vectors as my two vectors, I will find a vector that is orthogonal to the first normal vector and the second normal vector, which means that that vector is going to have to lie in both planes. And furthermore, it's going to specify the direction of this line. There's a lot of words. Okay, maybe go back 20 seconds and listen to that part again, just to get a little bit of intuition for what we're doing here. And I'll write it out also. Since L lies on both planes, it is orthogonal, perpendicular to both normal vectors, n1 and n2. Okay. That deserves an exclamation point. Big fact. We can get a vector, I'm going to call it V, call it whatever you want, parallel to L. We need a direction vector, we'll call it V, given by the cross product of those two normal vectors. So we're going to let V, you can do n1 cross n2 or n2 cross n1, it does not matter. Both of them are going to specify the correct direction of the line. n1 cross n2 is given by ijk. 1, 1, 1. These are the same normal vectors we did up in part A. So 1, 1, 1, and 1, negative 2, 3. Same planes we looked at before. Okay. So we get I times cross off first row, first column. We get 3 minus negative 2. Minus j. Cross off first row, second column. We get 3 times 1 would be 3. Minus 1 times 1 would be 1. Plus k. Do I have room? Let's see. Yeah, I do. times, cross off first row, third column, -2 times 1 would be -2, minus 1 times 1 would be -1. Okay, so we end up with 5, -2, and -3. Okay. So that's going to be our direction vector for the line. I'm going to make note of that. So this gives me a direction vector for L. And so finally, put it all together. Oops, go back to, there we go. Symmetric equations, that was what they asked for. Okay, we were using the point on the line. We found the one where it intersected the xy plane was 1, 0, 0. And we found our direction vector for the line is 5, -2, -3. So putting this all together, we get x minus 1 over 5 equals y minus 0. So y over -2 equals z minus 0. So z over -3. This right here, these symmetric equations, are describing this line of intersection right here in rainbow. Okay? So that is our line. Kind of a longer process than maybe you'd expect, but hopefully the conceptual pieces of that make sense and go right along with the calculations that we just did for you. Okay, go back, watch that one again. It's probably the toughest one from this section. Still a little bit more to this section. I think I'm going to save it for one more video. Should be a shorter one. We got to look at distance from a point to a plane. So we'll look at that next time. And then we'll also look at the distance between two parallel planes. So a cool little wrap up to this section. Okay. All right. I will see you in the next video. Happy mathing.